All right, today we're going to get right into it. We're dissecting the blueprints of a seriously impressive and highly profitable solar power plant out in Cairo in Tunisia. We're going to see how some really smart engineering choices, from the solar panels right down to the steel bolts, let this thing not only survive, but actually thrive in a pretty harsh climate. And get this, it's designed to pay for itself in just 5 to 6 years. Let's dig in. So, just how much power are we talking about here? The plant's capacity is 1.01 megawatt peak. Now that is a huge amount of clean energy. It's enough to make a real, tangible impact on the local grid. We're not talking about a small-time project. This is a serious piece of modern energy infrastructure. So here's our game plan for breaking this all down. We'll kick things off with the big picture, the overall blueprint for this unique environment. Then we're going to zoom in on the heart of the system, the solar modules themselves. After that, we'll look at the plan for sizing the whole thing, uncover its electrical nervous system, and finally we'll check out the skeleton that's built to hold it all together for decades to come. Okay, so let's set the scene. We're in the semi-arid climate of Cairo. The mission here was pretty ambitious, you know? They had to build a utility-scale solar plant that could perform at a high level, not just surviving, but really thriving under intense sun and high heat. And that required a very specific, super robust engineering plan. And that's really the key here, right? Every single decision they made, from the type of screw they used to the angle of the panels, was an answer to a challenge. How do you possibly maximize your power output while making sure the whole facility can take a beating from the elements and still be a smart investment for over 25 years? Well, that's exactly what this blueprint is all about. Now, let's get to the heart of the plant, the solar modules. I mean, a plant is only as good as its panels, right? This choice is the absolute foundation for everything else that follows. The engineers went with a specific technology called a bifacial module. And honestly, it's a total game changer. See, a normal panel just grabs light from the front, but a bifacial panel, it also soaks up the light that reflects off the ground onto its backside. It's just a brilliant way to squeeze every last drop of energy out of the exact same physical space. So why these specific Jinko modules? Well, they're using this advanced cell technology that gives them top-tier efficiency, which is crucial in Cairo's intense heat. They also degrade way slower over time, and because they're so powerful, you just don't need as many of them. That saves a ton of money on the structure, the cables, and all the maintenance. It really is the perfect heart for this project. So, once you've got the heart, you need a plan for the body. And sizing the plant is this critical balancing act. You've got to think about the land you have, the power you want to generate, and the technical limits of your equipment. It's all about finding that perfect, just right configuration. You know, the Goldilocks zone. And they didn't just guess or pull a number out of a hat, no way. The engineering team meticulously modeled 3 completely different scenarios: a minimal version, a nominal one, and an optimized one, just to see which one made the most sense, both technically and practically. And this table tells the whole story. The minimal setup with 1,390 modules, it got rejected because it didn't create a balanced electrical system. The optimized scenario, well, it was possible, but it was really pushing the limits of the land and would have needed more study. So the clear winner was the nominal scenario, 1,400 modules. It was technically sound, super robust, and became the recommended foundation for the whole project. So the big takeaway here is that the nominal scenario wasn't just a random number. It was the absolute best engineering compromise. It delivers fantastic performance, it's built on solid technical ground, and it even leaves a little room for flexibility later on. It's just the smart, reliable choice. Okay, so we've got the heart and we've got the plan. Now let's take a look at the plant's nervous system, that complex web that takes all that raw power from the panels and gets it to the grid where people can actually use it. The journey of an electron here is pretty simple, but it's incredibly powerful. First, those 1,400 modules collect sunlight, generating direct current, or DC power. Then 3 huge inverters do the magic trick of converting that DC into alternating current, or AC, which is what our homes and businesses use. From there, a transformer boosts the voltage, and boom, that clean power gets delivered right to the grid. And the specific components they chose are absolutely crucial. These high-power string inverters are the industry standard for plants this size because they're just so flexible and efficient. The transformer station was deliberately oversized, which means it can handle the plant's full output, even on the hottest days, and could even support future expansion. And placing it at the back of the site, that was a clever move to shorten cable runs, which cuts down on power loss and makes maintenance a whole lot easier. All right, let's get to our final piece, the skeleton. Now, this is not just a bunch of metal racks. This is a precisely engineered structure designed to hold millions of dollars of equipment perfectly steady through decades of wind and weather. We're talking about a quarter of a century. When it comes to this, durability is everything. These structures are designed and built following rigorous international Eurocode standards for structural and geotechnical engineering. I mean, nothing is left to chance. This skeleton is absolutely built to last. Let's look at a few key numbers that really define this skeleton. First up, 22 degrees. Now, that is not an arbitrary number. It's the precise calculated tilt angle for the panels in this exact spot on the planet. This angle maximizes sun exposure all year round, squeezing every single possible watt of energy from the sun. Next number, 3.5 millimeters. That's the thickness of the galvanized steel they used for the main vertical posts. This is literally the backbone of the entire structure. It provides the core strength needed to stand up to high winds and, well, the test of time. And now for a number that's tiny but makes a huge difference, 80 micrometers. That is the thickness of the hot dip galvanization coating on all the steel. Think of it like a protective shield, an armor that prevents rust and corrosion, making sure that structure stays strong for decades. And what does all this precision engineering add up to? Well, it adds up to an operational lifespan of over 25 years. That's right, the perfect angle, the strong steel, and that protective coating, they all work together to guarantee this plant will be a reliable source of clean energy for a whole generation. And this quote from the technical report, it just says it all, doesn't it? Every single choice, the bifacial modules, the nominal sizing, the electrical gear, the steel skeleton, was specifically selected and optimized for this exact location. It's a true masterclass in site-specific engineering. So we've basically seen the anatomy of a brilliantly designed power plant, where every single component works in perfect harmony. And it kind of leaves us with a final thought, doesn't it? This is the blueprint for one incredibly successful solar plant. So what will it take to make this kind of smart, durable design the blueprint for an entire region's energy future?